All right. So, James, let me make sure you get another invite. I think you have an invite though. Oh, you got it. Okay. All right. So we started talking about this concept of stuck on and stuck at fault. Stuck at 0 and stuck at 1 faults last week. So the whole idea is that it's always tied to ground or VDD no matter what. And not last week. We talked about this idea of controllability versus observability and how we can actually propagate a fault through a circuit and how we can use that to troubleshoot. We went over the cut in half method from the Naval Nuclear Power Program, where you make sure how you can actually verify that a circuit is working properly and how you can troubleshoot it down. And what I would like to do is I'd like to start here. So if you recall, we have these concepts of D and D bar. So D is when we expect a 1 and get a 0, and D bar is when we expect a 0 and get a 1. And so then we came up with all of the truth tables for AND, OR, and XOR and how that works. So as a result, what ends up happening is we have the controlling value means that 0 is going to always give us a 0 on the output. If we get any 0 on the input, that controls it. Likewise with an OR, if you get a 1, you're always going to get a 1 on the output. If you get a NAND, if you control it with a 0, and you're going to get a 1 on the output, and likewise if you invert with an OR. And so 6.3, we're going to use this full out of circuit example that we used to troubleshoot from before with the XOR at stuck at 0 fault for the second input. Show the composite logic for input combination 110. So what we have is that we have input combinations, right? And we're putting in a 1, we're expecting a 1, we're putting in a 1, expecting a 1, we're putting in a 0 and expecting a 0, right? So the XOR stuck at 0 fault for the second input, right? So what ends up happening is that when we get a stuck at 0 fault, right? If we have 1 and 1, we're expecting a 0, correct? But we're getting a 1 because this is stuck at 0. So what we end up getting is D bar. Right? Recall D bar is 0 and 1. So this way, and then this is the table. I'll show it again with the D and D bars propagated. So we have D bar here, and we're supposed to get a 0, but it's stuck at 0, right? So 0 and whatever this happens to be, we just propagate D bar. And then from here, what ends up happening is we're getting D bar on the second input of this NAND gate, right? And we're getting a 0, I'm sorry, AND gate. So no matter what, we're going to get 0 on this output here. So we get 1 and 1 here. And it means we get 1 and 1. We're expecting 1, we're actually getting 1. And then we have 1 and 1 on this output. So it's interesting, and why this is useful, let me scroll down to the second version of the solution, which is the same thing. What's interesting is that if we put 1, 1, 0 on the output, we're going to be expecting a 0 and getting a 1, but we're getting the correct value on this output, even though we're sending it to, even though D bar contributes to the second output. So that shows you how choosing specific inputs can propagate certain values to the output, but in other cases, you'll actually still get the right value, which is why we want to do these combinations and figure out which combinations we want to use in order to ensure that we can fully propagate values to the output. And when we come up with a minimum subset, and we're going to work on problems on like that today, what's going to happen is that minimum subset, we can propagate all the potential stuck at 0 and all the potential stuck at 1 faults. So does that make sense so far? So let me give you another one. Let's say I have 1, 0, 0. Right, so we have 0, 0 here. Actually, let me let's change this problem. Let's call it a stuck at 1 fault for the second input, and we're going to call this 1, 0, 0. So we have, the way you would work it is to be 0 and 0 there, but it's going to be 1 and 1, right? So if we get 1 and 0, we're expecting a 1, and we're actually going to get a 0 on the output, so we get D. So we get 0 here. D and 0 on an XOR is going to be a D on the output, like before. So we get D here. Sorry, we get D on the second input. Actually, you know what? I know how to make this problem even more complicated, but it will show the right idea. So let's make this 1, 0, 1. So we get 1, 0 here like before, so we get Cn is 1. This propagates here, so we get D and 1. So we get D and 1, what that means is we're expecting a 0 on the output, but we're getting a 1. Right? So that gives us 0 and 1. Likewise, we have C here, that gives us a 1. That means no matter what we put D, we're going to get, we're expecting D, and we're getting D, because we're expecting a 1, and but we're getting a 0, so D and D here, right? So then this is A and B, so we're getting 1 and 0, so we're getting 0 and 0. So D or 0 becomes D. See how it works? So it's the same fault with a different set of input combinations, or we have different, that'll give us a different output. So next we're going to say that we're going to present this algorithm. All right, so 6.12. Now I'm going to walk through this here, and we're going to describe the difference between the main test generation algorithm, the justification algorithm, and the propagation algorithm. Now it's probably, as you skim through it, it looks really complicated. When we go through example 4, I'm going to show you the whole thing here, and then what's going to end up happening is that you're going to see that it's actually pretty simple. So first, we set all values to x, and so we have an initial input. So also I have to make a really note. Let me start defining things. So we are trying to figure out a test for L stuck at V. So for example, we have a node stuck at 0 or a node stuck at 1. The line L is stuck at value 0. So the input to that first XOR gate is a stuck at 0 fault or stuck at 1. Okay? So we have a node and a value who are stuck at 0, stuck at 1. And so what ends up happening is that we set all values to x, and then we call this justify function where we pass in the node and the value bar, meaning if we're doing a stuck at 0 fault, we want to do stuck at 1. So let's go to justify. So we're going to set, so we have L and V, so the way the functions work, this is actually going to be V bar from previously, right? So we're going to set that node to the opposite value. So if it's a primary input, then we return. Now, what we're trying to do here is we're trying to see if we can control it. Okay? What that means is, so we set C as the controlling version value of L, right? So that if it's a primary input to a gate, such as, remember when we had like A and B, and we had that stuck at fault where it was initially an XOR, like so. We do stuck at 0. If it's a primary input, that would be this case. Anything else, like remember, so this one would be driving an AND gate. So it's this case, it's not a controlling input. So that means L is at a gate. That means we say that the controlling value of C of L, so I is the inversion of L. So the controlling value, what does this mean? The controlling value of the gate, we know that the controlling value of, the controlling value of AND is a 0, right? So if we put the stuck at fault on the output of this XOR gate, so this is stuck at 0, then this would be our L, right? This would be our line, and V would be 0, and that means V bar is 1. So since we've set L to V, that means we've set L is equal to 1, right? And C is going to be the controlling version of L. So if it's driving this gate here, then what's going to happen is the controlling value of the AND gate is 0. So C will be 0, right? And I is going to be the inversion of L. So that just means 0. So if we're going to say it's invalid, is going to be V XOR C, right? And so that's going to be equal, in this case, V is equal to 0, right? XOR C, which is going to be equal to 0. So if invalid does not equal the inversion of C, like it is in this case, so C invalid is equal to 0, and C is also equal to 0. So what we have here is now we're going to call for each input of the rest of this gate, input J of L. So now we're going to go all the way through these gates. We're going to keep calling justification. Now, if the reason why the algorithm is set up this way is because if it's on a line and we put in if we change it, that means that we're going to be able to control the circuit. If not, then we have to check the other lines of the gate. So if you have, in this case, we have the gate we just stuck at 0 fault. If we put a 1 on there, that if we had stuck at 0 fault, but if we was able to get through and put a 1 on there, that doesn't mean that we know what's happening with the AND gate, right? Because it's dependent upon the other inputs. If this was an OR gate, then what would happen is that it would end up working because the controlling value of L would be 1. So in that case, if it was an OR gate, we would have stuck at 0, we'd have the controlling value of is equal to 1. The inversion of L, we set L to V, remember, is stuck at 0, so V is equal to 1. So this means this is now equal to 0. V XOR C is equal to 1, which means the invalid does not equal C. Sorry, 1 XOR 1 is 0. And therefore we know that we have a controlling line, and therefore the line that we have, we can propagate that circuit. We can continue. Okay? Otherwise, if we had the situation I just described with the OR, select one input of J and justify invalid. So then once we do, and we're going to be working through a clearer example where I have the algorithm next to the actual circuit. So if V is equal to 0, then we want to do propagate the line and D. Otherwise, we want to propagate 1 D bar. And so propagate means we want to push, we're trying to push the L to the output. So we have this D, so let's say we're passing D here, right? D, we're going to set the line equal to the error. And if L is a primary output, then of course we're going to return because we know where the error is. Otherwise, K is going to be the output line of the gate driven by L. So we have an AND gate here, and we have L driving this line, then this would be K. So C is the controlling value of K, and I is the inversion of K. So either K is an output, or we have a controlling value. And for each input of J, which is this gate here, of K other than L, I'm sorry, input J of K other than L, then we want to run justify again. Right. So probably seems really complicated, but here's an example to show you what's actually works. So we have a situation here where we have no fan out and no sequential circuits, right? And we have that would be L stuck at V. So F is stuck at 0. And since it's stuck at 0, then what's going to happen, you can kind of get a general idea. That means whatever G is going to, it's just G, H is always going to be G, and then G, it's going to be, the output's going to be, G is equal to CD, right? So the CD is going to be E bar, so it's going to be C, D, E bar. But we need to be A or B, A and B, or C, D, and E bar. So we have wrong logic here. So here's what we do. First, remember we invert it. We have the main test generate, so we're trying to get this stuck at fault, stuck at 0 here. So what's going to happen is we invert the value and then pass it to justify, right? Because it's L and V bar. So what ends up happening is, remember the controlling value of the OR gate is the controlling value of the gate here is a 1, right? Was gate. If you have a 0 here, then it's propagated out. So the controlling value of the gate is 0. So it's 0. I is the inversion, if you recall from the algorithm here. I is the inversion of the line. So you have stuck at 0. I'm sorry, is the inversion of the line that we've passed. So we have 1 here. We have stuck at 0. We passed the inversion, and then I is going to be equal to 0. So remember that 1 V XOR C is going to be equal to invalid. And I guess this inval equals 1. And so we check, does inval equal C bar? So is it the opposite of the controlling line? And it is. Since it does, for each input J, we want to run J and then inval. So what we're doing here is that we're then going to run B. So we're running the previous gates. Since it's inversion, we want to make sure that we're getting all of the controlling signals of this previous gate. So what I've done to make it simpler is I've done this little chart. And so we have F stuck at 0, and then first we justify F equals 1, right? F and 1. So what that means is we go back here, right? The controlling value is 0. And if we want to figure out what this error is, so this is where all the algorithm is going to become and made into natural process. If I want to generate a 1 on the output, I need to get a 1, 1, right? So that's what's going on here. And the whole goal is we're trying to figure out what we need to do to get these values back and not have it written out when we get to J. Right? So then what we do, recall from the algorithm here, we're going to propagate the error. So if V is 0, then we're going to propagate 1 and D. So what we're doing is the L and D, sorry. So here we're propagating F and D, right? So we run the algorithm and we see that propagating along here to H. So we have to worry about F. We want to go forward to H to see if we can propagate the output, and we have to then see if G is contributing to hurting our ability to propagate it. So F is stuck at 0, so we want to propagate D here, right? So first, we want to say K is equal to H, so that K value is the line on the output of the gate being driven by the wire. So the previous ones, you're justifying it. We're justifying to see if we can propagate what values back on the input. So if we put 1, 1 here, we should get a 1, and then we'll immediately have a 0 on that error. See that? If we have 1 and 0, we'd actually get 0, and we would not be able to recognize it. So if you're struggling with the algorithm, the best way to say it, if this is a stuck at 1 fault, then what could be, this could be 0x or don't care and 0, because this will mean that we would, either of these two combinations should put a 0 on the output, and we'll get a 1 on the output, so we now know our error. So then we have to see, when we get here, we have to identify the wire that's on the output of the gate, and then we have to see the inputs of the gate to see how the inputs of the gate contribute how we can propagate it. Because we need to determine what the values are and how we can get an incorrect value on the output so we know that something's wrong. So that's where the propagate comes in. So we have this value k, the line, is equal to h here. We set c is equal to 1. And I is equal to not h. So c equals 1 puts 1 on the output. So we know the controlling value is 1 here, right? So if I have a stuck at 0 fault, what it means is that if I propagate D here, if I have a 1, well, it's going to put a 1 on the output, right? So that means that I can have so that means whatever G is, G can't be a 1. G has to be a 0 so we can propagate D further. So since G has to be a 0, what this justifying algorithm is saying is that, okay, that means we either have to have 0x or x0 on C or D. So we know that A and B have to be 1, and then it can be either of those. One of those two has to be a 0, but you can choose which one. So then here we've propagated D to this output there, right? Now, what's the controlling value of an AND gate? We know that it's 0. So we can't, if we have a 0 here, that means we're going to get a 0 on that output. So we have to invert it. So that way whatever D is gets put out there on the output, right? So then we have I, and then this this justify means we go, okay, what's the opposite value of here? This means it's going to be 0, which means our input, which means the input combination 1, 1, 0, 0, 0 will propagate the error. So here's how that algorithm works again, kind of intuitively. I know I have a stuck at 0 fault, right? So the inversion, right, means that I'm trying to figure out what the value is that creates the value 1 here. The values that creates the value 1 has to be 1, 1, right? Which is where this is coming in. Now the reason why I do that, 1, 1, is because if I get 1, 1, then I have to get 1 that I can recognize stuck at 0 fault. Now tying that back into the algorithm here, when I'm at justify, you see how it's go for each, for the AND gate, if they're not equal, that means I have to set all of the values in order to get a specific value on the output, right? If it was an OR gate, I only have to set one of them to get a 1 on the output. So the whole idea of this invalid equals the opposite of C is determine whether or not I need one input or all the inputs. So if this was an OR gate here, and I had a stuck at 0 fault on the output, that means this could either be 1 or 1, right? So if what I have to do is I'd have to get a 1 on the output. So that's why I do the inversion. And then the controlling value is a 1. So this value would be 1 here. So V XOR C is going to be 0, which means I have to select one of the lines. You see the difference there? Does that make the algorithm make more sense? Okay, good. I'm starting to get a little nods. Yeah. So then, but here in this case, we know that the XOR came out to be 0, to be 1. So therefore, we have to go through all of them. So this became 1 and 1. Would give us 1 here. So we have stuck at 0. And so here we're going to replace to propagate it. Since we have a stuck at 0, we're propagating D, right? It means we're expecting 1 and we're getting a 0, which is why we're propagating D. So again, here the controlling value is a 1, which means if I have a 1 here, then I would just propagate a 1 to the output. So what I need to do instead is I need to put a 0 there. That propagates D. And then what you're going to do is you do the justifying goes backwards and the propagating goes forwards. So what do I need to do to get a 0 on here? I need to either do 0. One of those two combinations will work. And then I have D. The controlling value of an AND gate is 0, which means if I put a 0 on any of the inputs of an AND gate, it'll automatically propagate the 0 to the output. We don't want that, so we need to put a 1 here, so that way we can get a D on the output. And then, well, I is 1, that means E has to be 0. Does that make sense? Cool. Okay. And so, in this case, we have that value there, right? So, and that is a typo there. That should say 0. The numbers put on the solution are correct. So on an exam, you do need to justify why it is that you chose what you did. Now, typically, it can be as simple as going through and just saying, okay, so that, if I work through that and I say, well, that has to be 1. The controlling value is 0, so it has to be 1, 1 to put it out there. Then it's 0, so I say it's D. But you have to do some sort of notation that you have to say that you justified and propagated it. Remember, justify is going backward, propagate is going forward. Okay, so here's where this becomes an issue. So this previous algorithm is a simple one for when we don't have fan out. Fan out causes issues. Why does it cause issues? Because if I have a stuck at one fault here, it becomes really difficult when I have multiple fan outs causing different issues. So if I had a stuck at one fault, right? That means it's D bar. So this is going to be a NAND gate, and the controlling value of a NAND gate is still 0. Right? Because you put a 0 on a NAND gate, you're going to get 1 on the output. So we have to have 1, 1, 1 here on this. So if you have that, what ends up happening is that you propagate a 1 here, and it goes to NOR. So if you put a 1 on a NOR, it's automatically a 0. Okay? You put a 1 here, you invert the 1, it becomes a 0 automatically, and you put a 0 on a NOR gate, so we propagate E to AND. Right? Now, here's the issue. We've got D bar. Now, D bar goes here. Now, normally what we would be doing is we would want this to be a 1, so that way whatever is put in on D bar is propagated to the output, right? So we would say this would be 1. Okay, so this has to be 1. Then we can say that's a 1, right? Oh, no, I'm sorry. If it's a 1, then they all have to be zeros. So we would say that. So that could work. But same thing, we have to have a 0 on this output here. Well, we put D bar here. We need a 1 here. Right? So D bar, we have to have a 0. Well, unfortunately, that means we have to have a 1 here. So if we need a 1 here, then both of these have to be 0. And that means that we can't generate this stuck at fault. See that? See how that works? So the result is the fan out, because it's going through multiple paths of the circuit, is making it difficult using just the justify and propagate algorithm to make it work. So there has to be another algorithm that we use. And I just described, everything I just described is there, so if you're reading it over, you can, I'll leave it there for a moment. And okay, so, and here I'm just basically justifying, like, well, I'm describing the other algorithm, so if you have no fan out, you can do this faster, because the D algorithm, which I'm about to show you here, takes a lot longer and a lot more overhead. So when I took a graduate course, my graduate course was to write in C a program that did the full D algorithm for, I think it had to be up to like an 8-input circuit. But if you implement it right, it works. so I said the same thing. Okay, so so everything I've just described is here. All right, so first we're going to talk about this backtracking strategy. So if you recall, I said there's backtracking and on the different circuit families. So this backtracking strategy allows us to incorporate for sequential elements and fan-out elements. So to searching for a vector, we have to do a decision process. So what's going to happen is the algorithm is going to deliberately make guesses. And then from there, you pick several alternatives for a line justification. You pick one alternative. If it leads to an inconsistency, then we're going to backtrack, and you're going to see examples here. Okay, so in order to understand the whole algorithm, we have to define 3 different terms, and then there are 3 steps of this implication process. So the first one, as we're defining it, is the D frontier. Okay? So the D frontier are all gates in a circuit whose output value is currently X. So remember we went through the circuit, we said everything is X, we don't know what it is, but have 1 or more error signals on their inputs. So we haven't propagated the value to the output yet, but we know what the input's going to, but we know that there's 1 or more error signals on those inputs. So the J frontier are all gates who the output value is known, but is not implied by the input value. So somehow we have figured out what the output is based on a different gate in the fan out, and because of that, remember in the other example we showed that we knew what the other gate needed to be, so we knew that the input to the inverter had to be 1, and therefore we had to choose it as a 0. So therefore that would be an example of a J frontier circuit. So 6.15, unique D drive, when only 1 gate remains in the D frontier. And that's going to be important when we start doing the actual algorithm. So the 3 steps of the implication process for the D algorithm. 1, we have to compute all the values that can be uniquely determined by the implication. So that means we're going to imply that this line should be a 1 or should be a 0. And then we're going to check for consistency inside the values. And then we're going to maintain the D frontier and the J frontier. So basically what's going to happen, and I'll show you this after 6.17, is the best way to do it is to develop a chart like this. But in that case, I'm going to walk through it. So the D algorithm, we have C is just the overall circuit that we're inputting. And so if you're writing a C code, what you would do is you would represent some sort of algorithm, and you'd have the notation for the circuit defined in a certain way. So you have inputs, gates, and so forth, and wires. So N is all the nodes. L is the specific thing, we believe the line that we have the stuck at fault, and V is what we're stuck at, so it's 0 or 1. So we're going to go through and we're going to set all the nodes in C initially to X. And we're going to add all the gates to this initially to this J frontier. And then we're going to set the node L equal to the value V. So while the primary output is X, so let's say I have an AND gate here, and I have we have stuck at 1 fault, right? So the primary output is X, since we've defined all the nodes to be X in the circuit before. Determine the implications and set values. So here, if it's 0, we'd have to propagate 0 to the output. If it's 1, we propagate 1 to the output. I'm sorry, if it's 0, it's 0, and it's 1, it's 1, right? We're going to check the results. If the check fails, determine the gate that caused the failure. And so what's going to happen is that we're going to say something is a certain value, and therefore we propagate through the circuit. And if we get a contradiction, then we know that a certain aspect is wrong. And then eventually, what we're going to do is we're going to get down to the point where we're going to start adding gates to the D frontier and the J frontier. For some reason, we have all the gates out of the D frontier. That means we can't find this fault with normal methods. And the J frontier, if we have it full or empty, that means we found the exact combination that we need. So here's our circuit, and we have several fan outs here. So we have B fans out to gate G3, we have A fans out to gate G1, C goes out to G5. Additionally, the output G, which comes out of this NAND gate, fans out to G2, G4, and G6. But then we have D fans out to both gates, G1 and G2, E fans out to gates G3 and G4, and F fans out to gates G5 and G6. So we have a lot of circuits here, right? So here are step one. So we have A is a stuck at 1 fault, right? So the best way to figure this out immediately is that we set it to 0. And therefore, H, we have a 0 on the input of a NAND gate, right? So that means H has to be 0, right? So we're propagating this, and we're going to get here. So if we have a 0 on the input of a NAND gate, I'm sorry, yeah, it means 1. I meant 1. So then if we have a 1 there, then we haven't determined what can be out there, because 1 is not the controlling value of a NAND gate. So that means we've added in our D frontier, we know which values are X. So here we have G1, G3, G5, and G7. We know that, okay, so in order to propagate this value on, right, we know that B and C must be 1, right? Because we can have 1, 1, 1, we would propagate D along. If it's 0 and 0, we wouldn't know. So that would be 1 here. So if we have 1, that means 1's going to be there, and C, that means 1 is going to be there. And so we have D, so we're expecting a 0 and getting a 1, so that would be D. So then what ends up happening is D goes here, D goes here, and then D goes there, right? And so if we have a 1 on the input, if we have a D, if we're expecting a 0 or getting a 1, well, if we're expecting a 0, we should always get a 0, right? If we're getting a 1, we don't. If we have put a 1 on there, we don't know. So it would be, we're expecting 1, but we're getting this value instead. So because of that, we have G2, G4, and G6 here, because we don't know yet in the D frontier. And we have G1, where we still have X here, G5, and G7. They still are undefined, so they are we either know them or are X, so they're on our J frontier. So next, we have H is 1 and A equals 0. So let's choose. So now we have to start choosing values to see if we can propagate, right? So we know that D is here. So if we have a 0, but we're getting a 1, if we want to propagate the output of D to the output of a G, we have a 1 here, right? 1 in D, so if it's 0, it would have been a 1, and 1, it would have been a 0. So it propagates D bar to the output. So if we choose D is 1, therefore D bar is 0, right? Well, if D bar is 0, that means we have A is equal to 0, right? And we should get a 1 here. So H is 1, so that means that value is correct. You see what I'm going on here? This takes G1 out of the J frontier, because now we have verified the correct outputs, right? And so he makes I is equal to D bar, which we've already defined here. And this puts G7 in the D frontier, because if we have a 1, we start having D bar. Now we start getting values there. Because if we have a 1, if we're expecting a 1 and getting a 0, then if we're getting a 0, then automatically it's going to be put on there no matter what. Step 3. So now we're going to start checking everything with E here. Since D bar is at I, right? The way to get the error to propagate to N. Yeah, let me delete everything. So we got D bar at I. So that's where we were at. The way to get the error to propagate to N through the NAND gate is to make all the other values 1. So I need J to be 1, I need K to be 1. Remember, I'm also propagating D bar here, right? And propagating D bar here. So what I need is I need all of these other values to be 1. Remember, H is already 1. So if I have a situation where I have B is 1, I have C is 1 here, and I have F and E, and we've already defined that D is going to be equal to 1. So we already know that D has got to be 1. So what happens? So if we are going to then say that we're going to choose, we need to get a value of E of, we need this value to be 1 on the output, right? So if you have 1, 1 on the output of a NAND gate, what do you get? Correct. So we want a 1 though, right? So E bar has to be 0, which means E has to be 1, right? So if we get 1 here, so 1 in D bar, what is 1 in D bar in a NAND gate? D, correct. Right? Which is not 1. So therefore, and so this is where I'll scroll down to the explanation so you guys can see what it is. So we have D as a 1 on the output. So we have an issue there. So here I'm describing E must be 0 and E bar must be 0 and E must be 1. Since G is an input of G4, it is all, and it is D, this makes K equal to D bar. However, we have defined K1, therefore it's a contradiction, right? So we know that we need this to be a 1 and we put a D there. So since E1 made the contradiction, let's start with E1 and find the implications. Right? So if E is equal to, if E is equal to 1, so what does that mean? This means that G3 is now removed from, so we already know that E is equal to 1, then we have this value here, right? 1 and 1, 0. Yeah, there we go, right? So then we have to imply what's going on here. So G3 is now removed from the J frontier. This means that K equals D bar, E bar equals 0, and J equals 1. So step 5, to see what the error propagates, we have to set L equal, sorry, let me try one more time here. We're going to set L and M equal to 1, right? So we have to set 1 and 1 here. So that means if we have F, C, G bar, right? So if we have C is equal to 1, and I need to propagate, so F has to be 0, that means F has to be 1. Make sense? So here's the thing, 1. And here I'm getting G down here, so that becomes D. And so if I have 1 and 0, I'm going to propagate D bar to the output. But that's a contradiction, so I need it as a 1, right? Make sense? So since F equals 1 makes the contradiction, let's start with F equals 1 and find the implications. So you find that if F equals 1, that makes M equal to D bar, F bar equal to 0, and L equal to 1. Kind of like what we found. G5 is out of the frontier and G6 is into the frontier. This means that the algorithm is solved. That means that if we have a 0, 1, 1, 1, 1, 1 for the input, we're going to figure it out. So here's what we're doing. So there's 0, 1, 1, 1, 1, and 1. So it just kept going through. So here's what happens. We get here, we get to, we're expecting a 0 and we're getting a 1. So you have D there, and D there. So you probably get 1 here, F bar is 0, E bar is 0, and D bar is 0, right? So here we have, on this input, we have 0, right? Now you get 0, 0, you get 1 here, which is what we want. We have 1 in D, so that gets D bar, right? So here we have B, which is 1. We get 1 in 0, which is 1. We have 1 in D, which is D bar. Same thing here, we have C is 1 and 0, so that gives us a 1. And then 1 in D, which gives us D bar. So that means is that any combination of NAND gate where you have 1 in D bar, we're going to get D. Which means we have successfully propagated the error to the output. So those contradictions mean that if we're getting the contradictions here that are the same, that's fine. And so the steps is that we started with A equals 0 because we knew this was stuck at fault. So the implications were A equals 0. That means the H1 had to be the output. Since A is 0 here, that means H has to be 1 on this NAND gate. So what I would recommend you do is I would write this solution out and then look at this circuit as you're looking at the video. And then so therefore we know that since H is 1, right? And we also know that B and C are 1 as well, which means that these inputs are 1, right? And because of that, G is going to be equal to D because we're expecting a 0 and getting a 1. So we've activated the fault and we have done a unique D drive through G, right? So that's what this unique D drive is. We've driven it to these outputs here. Okay. So G2, G4, and G6 have the error on the inputs and the undefined output. And then G1, G3, G5, and G7 are not like that, which is why we have our, you remember G2, G4, and 6, they're in the D frontier, and J frontier is G1, G3, G5, and G7. Next step, we went through and we did D is equal to 1, and the reason we chose D is equal to 1 is because we knew that this had to be, we had a 0 here. In order to get a 1 on the output, this has to be a 1, and therefore this has to be a 0. Yeah. Yep. D is equal to 1. Let me make sure I'm doing this right. Okay, so A is equal to 0, and we need a 1 on the output. That means D bar has to be equal to 1 and D is equal to 0. And therefore, we're going to propagate the value out through I. So what happens there is what we have is I'm losing my mind. What happened here? I had it right. 0. Oh no, 0, 0 and 0 is a 1. 1, okay, so yeah, so you basically, if you have 0, 1, okay, I see what I did here. So if you have 0, 1, that's still going to propagate the 1 to the output, right? The only time you're going to have a output of 0 here is if it's 1, 1. So you can have 1, 1 or 1, 0 there. So there's where the contradiction comes into play. So what ends up happening is if you had 0 and 1, this would become a 0, this would become a 0, and then it would be a 1 automatically on the output. Right? If you had a 0 here, this would make it a 1, right? And then 1 propagates whatever d bar is to the output, right? So we look for the contradiction. So here we would have 1 definitely. So you could either have 0 or d bar. So if you had an instance where you had a 0 and this propagates a 1, right? This comes from d bar. Then we have an instance where if e is equal to 0, right? Then we would have equal to 1, and then b would be equal to 1, so that would propagate a 0. So we want a 0 here, so we can get a 1 on the output. Put a 1 there, we get a 1 and d bar, and we're getting a 1 again. Now see what the issue is there? What do you think the major issue is there? We're not propagating the value to the output. So that would be why we want to use 1 here. So that way we get d bar. So we get d propagated, and then we propagate d bar here. See that? So you're either propagating, you're getting a value that is controlling. So in this case, if you put a 0 here, 0 is going to go through no matter what, right? If you put a 1 through here on a NAND gate, it's going to allow whatever error we put through here to go through. And that's our goal, which is why we choose it that way. Make sense? Okay, on that note, it is 1:50, and also there's no class on Friday. So enjoy your weekend. I have, as you can see, I have the debut video capture. Hopefully it actually